Ancient societies moved mountains without modern machines. Their greatest monuments were not just triumphs of engineering, but staggering feats of human organization. This is a journey across 30 ancient infrastructure projects, from deserts to jungles, where the real marvel is not the stone, but the symphony of coordinated effort behind it. You will discover the hidden systems of planning, labor, and logistics that allowed civilizations to redirect rivers, span continents with roads, and build wonders that still stand. How did a kingdom feed an army of workers carving a mountain into a city? What kind of society could align its streets with the stars? The answers reveal a forgotten truth about our past. What does it mean to build something meant to last 1,000 years? That symphony of coordination echoes from a single, silent giant. The Great Pyramid of Giza is the ultimate testament to ancient organizational power. For over 20 years, the Old Kingdom of Egypt marshaled resources on a scale that still defies easy comprehension. The core challenge was not just moving stone, but moving it with breathtaking precision. Each of the roughly 2.3 million limestone blocks, some weighing as much as 2.5 tons, needed to be across the Nile, and then lifted into a perfect geometric form, rising 480 feet into the desert sky. This was not a chaotic scramble of forced labor. It was a state-run project of immense sophistication, a national endeavor that required the seamless integration of an entire society. The logistics alone were staggering. Quarrying the stone was a precise science, with workers using copper chisels and stone hammers to cut blocks along natural fault lines. But then came the journey. How do you move a 2-ton block of stone from a quarry miles away to the construction site? Evidence suggests a system of sledges, lubricated with water or mud, pulled along specially prepared causeways by large teams of men. This required constant coordination. The workforce, estimated to be around 20,000 skilled laborers at any one time, was not a permanent, suffering mass. Research points to a rotational system. Farmers, who made up the bulk of the population, would work on the pyramid during the Nile's annual flood, when their fields were underwater and agricultural labor was impossible. This was a form of national service, a duty to the pharaoh and the gods, supported by the state. We know this because of the remnants of the workers' own lives, found not in grim pits, but in planned settlements like the village at Giza. These were not slave quarters. Archaeologists have uncovered bakeries capable of producing thousands of loaves of bread daily, large-scale fish processing areas, and evidence of medical care, including set bones and surgical procedures. The workers were fed a diet of bread, beer, fish, and meat, rations calculated and distributed with bureaucratic efficiency. This was a highly structured, almost corporate operation. Labor was divided into crews, each with a name like Friends of Khufu or Drunkards of, a sense of team identity that fostered pride and efficiency. The pyramid, therefore, stands not as a monument to oppression, but to the astonishing ability of an early civilization to organize, feed, motivate, and house a vast temporary population for a single, transcendent goal. It is the physical result of a society that could plan for decades, manage complex supply chains, and align the labor of thousands toward a shared vision of eternity. That same principle of coordinated effort, applied not to a single monument, but to the arteries of an empire, flowed through the Roman aqueducts. If the pyramid was a singular crescendo, the aqueducts were a sustained symphony of logistics, playing out across hundreds of miles. This was not a single project, but a vast, interconnected network that brought life to the heart of the Roman world. To supply a metropolis like Rome, with its population swelling to over 1 million people, required more than local wells and the Tiber River. It demanded a permanent, engineered solution. The genius of the aqueducts lies in their relentless, invisible consistency. They were gravity-fed channels, meaning the water source, often a spring in distant hills, had to be higher than the destination city. This created an immense puzzle of topography. Surveyors, known as walked the proposed routes for hundreds of miles, using simple but ingenious tools like a kind of leveled water trough, to measure gradients with astonishing accuracy. The required slope was often less than 1 foot of drop for every 1,000 feet of distance, a gradient so gentle you could barely perceive it, yet it had to be maintained over vast, uneven landscapes. This is where the organizational coordination becomes breathtaking. To maintain that perfect, gentle downhill flow, the Romans had to become masters of the terrain. When they encountered a valley, they built soaring arcades, like the Gard in France, which stand as monuments in their own right. When they hit a hill, they tunneled straight through it. The Aqua, one of Rome's longest aqueducts, ran for 56 miles, and over 10 of those miles were in dark, hand-cut tunnels. This work required armies of skilled laborers, from stonecutters and bricklayers to mortar mixers and lead pipe fitters, all operating under a standardized set of engineering principles that were replicated from Britain to North Africa. The imperial administration provided the backbone. This was a state-funded, centrally planned endeavor. A dedicated corps of architects and engineers, often military veterans, oversaw the projects, and a permanent civil service was established to maintain the system. They managed a workforce of slaves, paid laborers, and state employees who constantly inspected the channels, cleared sedimentation, and repaired leaks. The water itself was meticulously managed, with distribution tanks called dividing the flow for public fountains, bathhouses, and private residences, according to a strict hierarchy of need. The aqueducts, therefore, were the physical manifestation of Roman administrative power. They required the empire to think in terms of systems, not just structures. It was a decades-long investment in logistics, standardized knowledge, and bureaucratic oversight, all to perform a simple, vital task: make water flow uphill toward civilization. This network did not just supply water, it enabled the very concept of the Roman city, with its public baths, its sanitation, and its dense urban life. It was infrastructure as a promise of order, a concrete declaration that the empire could reshape geography itself to serve its people. While Rome mastered the flow of water, another civilization undertook a project to control the flow of people itself, a project so vast it stitches itself across the very skin of a continent. The Great Wall of China is not a single wall, but a sprawling, multi-generational conversation in stone and earth, a testament to organizational endurance that spanned centuries. Its story begins not with unity, but with division. Centuries before the first emperor, rival warring states in ancient China built their own separate walls of rammed earth for protection against each other and northern nomadic groups. These were regional projects, impressive but disconnected. The first staggering act of coordination came with Qin, the unifier of China, in the 3rd century before the Common Era. He ordered these disparate walls to be linked and extended, a task of unimaginable scale that demanded the mobilization of a newly conquered population. Soldiers were the backbone, but they were joined by vast conscriptions of peasants and laborers, including scholars and prisoners, all pressed into service under a harsh, centralized mandate. The human cost of this early phase was immense, a hardship woven into the very folklore of the wall. Yet, this was only the first chapter. The wall we recognize today, the majestic stone serpent with its watchtowers snaking across mountain ridges, is largely the work of the Ming dynasty, starting in the 14th century. The Ming project was a consolidation of breathtaking ambition. They replaced crumbling earthworks with stone and brick, building a fortified barrier over 4,000 miles long. The logistical challenge here was not just about labor, but about supply chains in impossible terrain. Think of the problem. You need to build a stone fortress on top of a remote, windswept mountain. How do you get the materials there? Every brick, every stone, every bag of lime mortar had to be transported up sheer slopes. In some areas, teams of laborers formed human chains, passing materials hand over hand. In others, they used mountain goats and donkeys, or even waited for winter to slide materials along frozen pathways. The Ming administration established a military colony system, where soldier farmers were stationed along the wall to both defend it and sustain its construction, growing food locally to reduce the burden of long-distance supply. But the wall was more than a barrier, it was a nervous system. Its true function depended on a communication network as sophisticated as its masonry. Dotting the wall at visual intervals were beacon towers. These were not just lookout posts, they were signal stations capable of transmitting messages across vast distances at incredible speed. Using a code of smoke signals during the day and lantern fires at night, a warning of invasion could travel hundreds of miles in a matter of hours, far faster than any horse or runner. This required perfectly coordinated timing, standardized signals, and guards who maintained a constant, vigilant watch. The wall, therefore, was a living infrastructure. It was a project that consumed dynasties, demanding not a single burst of effort but a sustained, organized will across generations. It merged military strategy, civil engineering, and communications technology into one continuous line of defense. It stands as a physical ledger of imperial power, a record of how a civilization attempted to define its borders, not on a map, but in stone and sweat across the very bones of the land. But a wall is a fixed line, a statement of separation. To truly unite a continent of staggering diversity, you need a network of connection, a system of veins that allows the heart of an empire to feel the pulse of its farthest extremities. This was the genius of the Inca road system. Stretching over 24,000 miles across some of the most extreme geography on Earth, this was not merely a path. It was the central nervous system of the largest empire in the pre-Columbian Americas, a masterpiece of administrative control woven directly into the spine of the Andes Mountains. The sheer variety of terrain it conquered is almost incomprehensible. This network did not go around obstacles, it mastered them. Where it met a vertical cliff face, Inca engineers cut stairways directly into the rock. Where a mountain ridge blocked the way, they carved tunnels. To cross the deep, roaring gorges that slice through the highlands, they performed what might be their most astonishing feat, the suspension bridge. These were not permanent stone structures, but dynamic, organic creations made from woven grasses. The strongest fibers were braided into massive cables, some as thick as a human torso. These cables were stretched across the chasm and woven into a walking surface, with handrails of lighter rope. What's truly remarkable is that this was a scheduled communal responsibility. The maintenance and annual renewal of these bridges was a mandatory labor duty, or for nearby villages. The entire community would participate in the ritual of rebuilding, ensuring this vital link was always fresh, always strong. This principle of collective duty was the engine of the entire road system. The empire known as, or the Land of the Four Quarters, was a patchwork of hundreds of different cultures and languages, conquered over a remarkably short time. The road was the tool that bound them all together under the rule of the Inca in the capital. It allowed for the rapid movement of the imperial army, a deterrent to rebellion. It facilitated the flow of tribute goods, like textiles, food, and precious metals, from the provinces to the state storehouses. But its most elegant feature was its communication system, the runners. Imagine a relay race that never stopped, operating 24 hours a day across an entire continent. Along the road, at intervals of about 1.5 miles, were small stone huts called tambos. A highly trained and athletic young man would wait at his post, watching the horizon. The moment he saw the next runner approaching, he would sprint out to meet him, receive the verbal message or small quipu, a knotted string recording device, and then take off at full speed toward the next tambo. In this way, a message or a fresh piece of seafood from the coast could travel the over 1,000 miles from Quito to in under a week, a speed unmatched until the invention of the telegraph. This system required flawless synchronization and an immense human investment, all managed by a centralized, top-down bureaucracy that could mobilize labor and resources with stunning efficiency. The therefore was the physical manifestation of an idea, the idea that an empire could be woven together not by homogeneity, but by connection. It respected the brutal reality of the Andes, not by flattening it, but by threading a line of order and communication across its peaks and chasms. It turned impossible geography into a web of control, proving that the greatest infrastructure is often that which makes distance irrelevant. That web of connection, vital for an empire, finds its earliest echo in a more fundamental human need, the need to make the land itself provide. Long before empires spanned continents, the first cities were born from a simple, desperate bargain with two unpredictable rivers. In the Fertile Crescent, between the Tigris and Euphrates, the Sumerians faced a paradox. The land was flat and rich, but the rivers that watered it were both a lifeline and a threat. Their floods were violent and untimely, arriving not in the planting season, but during the harvest, capable of washing away an entire year's labor in days. The droughts in between could be just as catastrophic. To survive here, to thrive here, required more than farming. It required a radical reorganization of society itself to perform a single monumental task, the taming of the waters. The solution was a landscape-scale intervention, the creation of vast, artificial arteries. They dug immense irrigation canals, some stretching for dozens of miles, to redirect river water to fields that would otherwise be barren. This was the world's first large-scale civil engineering project, and it demanded a new kind of human cooperation. Someone had to plan the course of these canals, which required a basic understanding of surveying and gravity to ensure a steady, gentle flow. Then, the digging began, an endeavor of staggering manual effort. This was not a job for individual families. It required the coordinated labor of hundreds, perhaps thousands, of people from across the community, working with simple tools of wood and stone to move mountains of earth. But here lies the true organizational breakthrough. Digging the canal was only the beginning. The ongoing challenge was maintenance and fairness. A canal is a living system. It silts up, it breaches, its banks erode. Keeping it functional required constant communal upkeep, a shared duty that bound the community together year after year. More critically, once the precious water was flowing, who had the right to use it? The farmer at the head of the canal could easily divert it all, leaving those downstream with nothing. This potential for conflict threatened the entire social order. Out of this necessity, the Sumerians invented something as revolutionary as the canal itself: systematic law and governance. They developed some of the earliest known legal codes, like the Code of Ur, which explicitly laid out rules for water rights and penalties for damaging a neighbor's canal. A specialized bureaucracy emerged, with officials appointed to oversee water distribution, to schedule irrigation turns, and to adjudicate disputes. This was the birth of the temple and palace economy, where central authorities coordinated labor, collected surplus grain as a tax, and redistributed resources to fund public works and sustain the specialists, like scribes and priests, who made this complex system possible. The irrigation canal, therefore, was more than a ditch in the ground. It was the first blueprint for civilization. It forced scattered villages to organize into city-states, to surrender some individual autonomy for collective security, and to develop the rules, roles, and records that define a structured society. The wheat and barley that fed the first cities grew not just from mud, but from a profound social contract, an agreement to work together to bend the forces of nature toward a common harvest. The logic of the grid, of order imposed upon chaos, finds its expression not in a wall or a road, but in a city built from a single, visionary blueprint. In the highlands of central Mexico, the ruins rise from the valley floor with a geometric perfection so severe it feels otherworldly. This was not a city that grew organically over centuries, twisting with the needs of its inhabitants. It was, from its very foundation, a monumental act of will, a vast urban machine constructed according to a master plan of astonishing ambition. At its heart lies the Avenue of the Dead, a central artery over 2 miles long and 130 feet wide, running with celestial precision from the Pyramid of the Moon in the north to the complex in the south. This was the spine of the city, and every other element was aligned to it. The avenue is flanked by hundreds of precisely spaced residential compounds and temple platforms, creating a rigid, grid-like street plan that organized the lives of over 100,000 people. But the alignment goes far deeper than street corners. The entire city is a terrestrial map of the cosmos. The Pyramid of the Sun, the massive structure that dominates the eastern side of the avenue, is not placed randomly. Its western facade is aligned to set directly in front of it on two specific days of the year, signaling solar events that would have held profound ritual significance. The Pyramid of the Moon, at the northern terminus, frames the sacred mountain behind it, tying the built environment to the natural one. This was urban planning as a sacred act, a deliberate effort to create a physical model of a cosmological order. To execute this vision required a level of state coordination that rivals any ancient empire. The primary building material was a porous volcanic rock from the surrounding hills. This was not a haphazard collection of stones. The stone was shaped into standardized blocks, and the city's construction required millions of identical adobe bricks, all produced to a uniform size and composition. Think of the supply chain needed for this. You need consistent clay sources, vast pits for mixing, drying yards, and a system of transport to move these fragile, heavy bricks to construction sites across the city. This points to a highly organized, perhaps state-controlled production system. The labor force was immense. The Pyramid of the Sun alone contains over 2 million tons of material, all assembled without the wheel, metal tools, or pack animals. This was not the work of a few seasons. It was a generational project, likely coordinated through a system of labor obligations, where communities contributed their effort to the central authority in exchange for the right to live within this grand cosmic diagram. The residential compounds tell a fascinating story of this social organization. They are not divided into rich and poor districts in a traditional sense, but are instead remarkably uniform in their quality of construction. This suggests a society where status was expressed differently, perhaps through ritual knowledge or civic role, and where the state ensured a baseline standard of housing for its vast population. Stands as a mystery, a city whose original name and the language of its builders are lost to us. But its silent stones speak volumes. They tell of a civilization that could conceive of an entire city as a single architectural unit, align it with the heavens, and then muster the coordinated human effort for over a century to make that celestial blueprint a stone and mortar reality. It is the ultimate testament to the power of a unified idea, made manifest through relentless, organized labor. A cosmic city plan is a declaration of order, but an empire is a living, breathing organism that must be fed information. For the sprawling Achaemenid Persian Empire, the largest the ancient world had ever seen, this was the paramount challenge. Stretching from the Indus River to the Aegean Sea, it encompassed dozens of cultures, languages, and terrains. How could one man, the king of kings in his palace at Susa, possibly govern such a vast and varied realm? The answer was not just written in law, but paved in stone and packed earth, a ribbon of control stretching over 1,500 miles. This was the Royal Road, the information superhighway of antiquity, and its creation under the first was in administrative logistics. The vision was breathtaking in its simplicity and ambition. The road connected the administrative capital of Susa in modern-day Iran to the wealthy regional capital of Sardis in western Turkey. But this was no meandering trade path. It was a state-engineered highway, deliberately planned for one primary purpose: speed. Surveyors charted the most direct possible route across mountains, plains, and rivers, and then teams of laborers set to work standardizing it. They cleared the path, leveled uneven ground, and in some areas even paved sections to withstand weather and heavy use. To cross rivers, they built permanent bridges, ensuring the route was never interrupted. This physical infrastructure was only the skeleton. The true genius lay in the system built upon it. At regular intervals, approximately every 15 miles, the state constructed way stations. These were not inns for the public, but official relay posts stocked with fresh horses, supplies, and a dedicated corps of royal couriers. Here, the organizational coordination reached its peak. A messenger, carrying sealed dispatches from the king, would ride at a gallop to the next station. Upon arrival, he would not rest. He would immediately hand his dispatches to a fresh, waiting courier mounted on a fresh, rested horse, who would then sprint to the next post. In this relay, messages could travel the entire length of the road in just 7 days, a journey that would take a normal caravan 3 months. The Greek historian Herodotus immortalized the courier's motto, that they were stopped neither by snow, nor rain, nor heat, nor gloom of night. This was not poetry, but a statement of bureaucratic reliability. The system required an immense support network. Each way station had to be perpetually stocked with grain, fodder, and replacement horses. This demanded a complex supply chain, likely funded by imperial taxes and managed by local satraps or provincial governors, who were responsible for their section of the road's security and maintenance. Guard posts were established to protect against bandits, ensuring the safe passage not only of messengers, but of the imperial treasury, traveling officials, and most importantly, the rapid deployment of the king's armies. The royal road, therefore, was the ultimate tool of imperial control. It compressed time and space, allowing the central authority to sense disturbances and project power to the farthest provinces with unprecedented speed. It turned a collection of conquered territories into a unified, responsive organism. The paved path was just the visible sign. The real infrastructure was the invisible, clockwork system of men, horses, and administration that made the empire think and act as one. A different kind of line was being drawn across a continent, not for travel or defense, but for a purpose we can only guess at. Far to the south, on the stark, wind-scoured plains of Peru, the culture created an art gallery so vast it can only be seen from the sky. The lines are hundreds of enormous designs etched into the desert floor, depicting animals, plants, geometric shapes, and miles-long straight lines that run to the horizon. The mystery of their purpose, whether an astronomical calendar, a ritual pathway for deities, or a map to water sources, often overshadows the equally profound mystery of their creation. How do you draw a perfect hummingbird over 300 feet long or a spider with anatomically correct leg joints on a canvas of barren earth without ever seeing the full picture? The technique itself was deceptively simple, a testament to clever problem-solving. The desert is not sand, but a plateau covered in a layer of dark, oxidized pebbles. Beneath this dark veneer lies a lighter-colored subsoil. To create a line, the builders simply removed the top layer of dark stones along a predetermined path, exposing the bright earth beneath. The contrast creates the visible design. This process, however, required immense and coordinated labor. A single line, like the nearly 9-mile-long straight track, required teams of people to meticulously clear thousands of tons of stones along a perfectly straight path. For the complex biomorphs, like the condor or the monkey, the challenge was geometric. The design had to be scaled up from a small model to a monumental size without distortion. Researchers believe they used a system of stakes and ropes. A master design, perhaps laid out on a small scale, would have its key points translated to the desert using a central axis line. From this line, teams would measure out distances at precise angles, placing stakes to mark the contours of a tail, the curve of a wing, or the spiral of a monkey's tail. This was not random scratching. It was a large-scale surveying project, requiring a shared understanding of measurement and geometry among a large group of workers. The organizational effort points to a society with a strong central authority, likely religious in nature, capable of mobilizing and directing a workforce for projects that offered no immediate, practical return. This was labor for a transcendent purpose. The workers clearing stones in the searing sun would have only seen a trench at their feet, a confusing fragment of a curve or line. They had to trust the plan and the coordinators who held the vision of the entire glyph. The true form of their work, the majestic hummingbird or the watchful spider, was invisible to them, a secret held by the landscape itself, revealed only when viewed from the elevated foothills or, as we see it today, from the air. The lines, therefore, are a paradox. They are the most fragile of the ancient infrastructures, just a rearrangement of surface stones, yet they have endured for over 1,000 years because the desert climate is so still. They represent a different kind of coordination, one devoted not to practical necessity, but to faith, cosmology, and the human desire to leave a mark so large it could only be meant for the eyes of the gods. While the aqueducts carried the lifeblood of water, the Roman Empire moved its muscle and mind along a different kind of artery. The Roman road network was the terrestrial skeleton upon which the entire body of the empire was built, a web of all-weather highways that made the vast distances between provinces feel manageable, even routine. This was not a collection of muddy trails. These were engineered thoroughfares, built to last centuries and to move legions, messengers, and merchants with relentless efficiency. The famous saying, "All roads lead to Rome," was not just a metaphor, it was a statement of political and logistical reality. Every major highway was calculated to connect back to the golden milestone in the Roman Forum, the symbolic center of the world. To achieve this, the Romans developed a standardized construction technique so effective its basic principles are still used today. First, surveyors, often from the military, would plot the possible route, famously avoiding curves even if it meant cutting through hills or building embankments across marshes. Then, construction began with the fossa, a trench dug several feet deep. This was filled with a foundation layer of large stones, On top of this came a layer of smaller stones mixed with cement, followed by a nucleus of gravel, sand, and lime. The final surface was the dorsum, a carefully fitted layer of polygonal stone blocks that created a slightly cambered, durable roadway designed to shed rainwater into drainage ditches on either side. The result was a raised, solid highway that could withstand heavy traffic and the worst weather, turning a journey that might have been a seasonal ordeal into a year-round possibility. The primary builders of these roads were the Roman legions themselves. When not at war, the army was an enormous, disciplined workforce of engineers and laborers. Building roads served a dual purpose. It kept the troops occupied and physically fit, and it directly enhanced the empire's military capacity. A road built by a legion was, by design, a road that could quickly bring that very legion back to any point of crisis. This military origin is why so many roads ran arrow-straight, facilitating rapid marches and clear lines of sight. Behind this physical labor was an immense administrative framework. The planning of major routes was a central government decision, often initiated by the Senate or the emperor for strategic reasons, to secure a new province or to stimulate trade in a region. Once a route was decreed, the task of securing materials fell to provincial governors and local authorities. Quarries were opened, forests were cleared for timber, and contracts were issued. Maintenance was a perpetual obligation, funded by tolls and local taxes, and often assigned as a civic duty to communities living along the route. This system created a self-reinforcing cycle of control. The roads allowed for the fast deployment of troops to quell unrest. They enabled the efficient collection of taxes, as goods could be transported to central warehouses. They carried the imperial post, a state-run courier service with its own way stations and change of horses, mirroring the Persian system but on an even denser network. And perhaps most importantly, they facilitated the movement of people and ideas, allowing Roman law, Latin language, and architectural styles to seep into every corner of the empire. The Roman road was more than a path, it was a tool of integration. It physically and psychologically shrunk the empire, turning disparate conquered lands into connected provinces. It was the ultimate expression of Roman pragmatism, a durable investment in unity that whispered a simple promise to every citizen, from Britannia to Syria: you are connected, you are reachable, you are Roman. But a road is a line of control, a statement of human will over distance. In the jungles of Southeast Asia, an entire civilization performed a far more delicate act of coordination, one that required bending not just earth, but the very rhythm of the sky itself. The city of Angkor was not built upon a river, but upon a monumental idea that a society could capture the monsoon and make it bow to a calendar of planting and harvest. To understand Angkor is to look past its breathtaking stone temples like Angkor Wat and to see the vast, liquid engineering that made them possible. The Khmer Empire's capital was the heart of a hydraulic city, a metropolis sustained by the most ambitious water management system of the ancient world. The central challenge was the tropical climate, with its brutal dichotomy, torrential rains for half the year and parching drought for the other. To feed a population that may have exceeded 1 million people, the Khmer needed to grow rice, a crop that demands precise control over water, lots of it during the growing season, and carefully drained fields afterward. Their solution was to transform the entire landscape into a giant, managed watershed. At the core of this system were the immense, rectangular reservoirs built with earthen dikes. The largest, the West, is a staggering 5 miles long and 1.5 miles wide, holding over 50 million cubic meters of water, an artificial lake built by hand. But these reservoirs were not just passive storage tanks. They were the anchors of a vast, interconnected network of canals, moats, and embankments that stretched for hundreds of square miles. This network served three critical functions. First, during the violent monsoon rains, it acted as a flood control system, channeling excess water away from the urban center and into preventing the city from drowning in silt and runoff. Second, during the long dry season, the stored water was released through a carefully graded system of canals to irrigate the sprawling rice paddies that surrounded the city, allowing for multiple harvests each year. And third, the system had a profound symbolic purpose. The moats surrounding the temples were not just defensive, they represented the cosmic ocean, and the temple mountains at their center were the home of the gods, a microcosm of the universe made possible by controlled water. The coordination of labor to build and maintain this system is almost beyond comprehension. The excavation of the West alone required moving millions of cubic yards of earth. This was not the work of slaves under a whip, but a form of organized labor duty, likely tied to religious obligation and administered by a powerful central authority. Thousands of workers, using simple baskets and tools, would have moved in coordinated teams to dig the basins and build the towering embankments, which still stand today. The true sophistication, however, lay in the hydrological engineering. The entire system relied on gravity. The Khmer engineers mastered the subtle topography of the land, laying out canals with precise, gentle slopes to ensure water would flow where it was needed, when it was needed. They built sophisticated control structures, like stone spillways and water gates, to manage the flow between different parts of the network. This required a deep, empirical understanding of hydrology, gained over centuries of observation and trial, and it demanded a centralized planning authority that could think in terms of decades, even centuries. The system was not static. It evolved over 500 years, with each king adding new canals, expanding the hydraulic machine. This long-term vision is what made Angkor possible. The stone temples were the spiritual pinnacle, but they were built upon a foundation of mud, water, and breathtakingly organized human effort. The city was a machine for living, a delicate man-made ecosystem that turned the chaotic fury of the monsoon into the predictable rhythm of agricultural abundance, proving that the greatest temple a civilization can build is sometimes the one that feeds its people. Water, controlled and channeled, was the lifeblood of the Khmer Empire. Yet 1,000 years earlier and half a world away, Another island civilization mastered water in a completely different way, not for agriculture, but for the very comfort and sanitation of urban life. On the sun-drenched island of Crete, the Minoan palace of Knossos reveals a sophistication that feels startlingly modern. This was not a fortress or a solemn temple complex, but a vibrant, multi-level administrative and cultural center, a labyrinthine structure housing thousands. Its grandeur lay not just in its painted frescoes and storerooms, but in something far more fundamental, an invisible network of cleanliness flowing beneath the feet of its inhabitants. The palace's layout was an intricate puzzle of over 1,000 rooms spread across several stories, connected by a complex system of corridors and staircases. To bring light and air into the heart of this dense structure, the Minoan architects designed clever light wells, open shafts that channeled sunlight down to the lower levels, creating a bright and ventilated environment. But the true engineering marvel was hidden underground. Knossos possessed one of the most advanced drainage and sewer systems of the ancient world. This was not a simple ditch. It was a carefully planned, integrated network of pipes, stone conduits, and underground channels that served the entire palace complex. Think about the level of foresight this required. From the very first stages of designing the palace, the architects had to plan for the flow of waste and rainwater. They engineered a gradient throughout the entire structure, so that water from bathrooms, from kitchens, and from courtyards would naturally drain downward. This was then channeled through a main sewer, constructed from interlocking stone slabs, that ran beneath the corridors and out of the palace to a distant disposal area. They even had settling tanks, where heavier solids would drop out before the water continued on its way. For fresh water, they built aqueducts that brought spring water from miles away, storing it in large cisterns within the palace walls. This integrated system demanded a remarkable coordination of skills. The project required not just architects, but hydraulic engineers who understood gradients and flow. It needed teams of specialized craftsmen to manufacture the standardized pipes, which were tapered to fit snugly together, and stonecutters to shape the precise channels. Most impressively, it required a centralized authority with the vision and resources to insist on such a comprehensive public health infrastructure from the outset. This was not an addition, it was foundational. The result was a level of urban sanitation and convenience that would not be seen again in Europe for over 1,000 years. It speaks of a society that valued communal well-being, that understood the link between cleanliness, health, and a functioning, dense population. The famous myth of the Minotaur's labyrinth may capture the imagination, but the real maze of Knossos, the one that truly sustained its civilization, was built not of stone, but of water, foresight, and brilliantly coordinated civic planning. The comfort of a palace sewer speaks to a society settled in its own land, but the lifeblood of empires often flowed across vast, empty spaces between them. For the merchants who dared to traverse the Silk Road, the greatest danger was not bandits or harsh terrain, but the sheer, consuming emptiness. A journey from the markets of Baghdad to the gates of En could take over a year, crossing deserts where water was a rumor and mountains where passes were choked with snow for months. To make this flow of silk, spices, and ideas possible, an invisible network of support had to be woven into the landscape itself. This was the world of the caravanserai, the fortified that turned a perilous track into a viable commercial highway. These were not simple inns, they were logistical hubs, miniature fortresses of hospitality built at intervals of roughly 20 to 30 miles, a distance a loaded camel caravan could cover in a single day. Their placement was of geographic intelligence. Planners had to identify every reliable water source, every defensible pass, every natural stopping point along routes that stretched for thousands of miles. Building a caravanserai in the desert or the Pamir Mountains was an act of profound commitment. It meant transporting stone, timber, and mortar into the middle of nowhere and assembling a permanent, self-sufficient outpost where before there was nothing. The standard design was both practical and symbolic. A high, windowless outer wall provided security against raiders. A single, heavy gate offered a controlled entrance. Inside, a large central courtyard allowed hundreds of camels and pack animals to be unloaded, and surrounding this courtyard were arched alcoves and stables for the animals, and a second story of small, Spartan rooms where the merchants, drivers, and guards could find shelter. The caravanserai was a complete ecosystem. It had a mosque for prayer, a bathhouse for washing away the dust of the journey, and often a small market or repair workshop. But its most critical function was provisioning. The station master had to maintain stores of grain, fodder, and fresh water, not just for the staff, but for the unpredictable arrival of a caravan that might include 200 men and 500 thirsty animals. This required a complex, anticipatory supply chain. Local villages might be contracted to deliver supplies, or taxes from regional governors might fund the caravanserai's stores. The coordination was a public-private partnership on a continental scale. While many were built and funded by powerful rulers like the Seljuk Turks or the Safavid Shahs to stimulate trade and project imperial benevolence, their operation relied on a decentralized network of caretakers, cooks, guards, and animal handlers who lived in these isolated posts. Their existence created a rhythm of safe passage. A merchant could embark on a journey knowing that at the end of each exhausting day, a secure haven awaited, a place to rest, trade news, and prepare for the next leg. This system of organized hospitality did more than move goods, it moved people and cultures. In those shared courtyards under desert stars, Persian astronomers compared notes with Chinese scholars, Byzantine coins were exchanged for Indian gems, and languages blended into the lingua franca of commerce. The caravanserai was the physical node that made the Silk Road a network, not just a route. It was a promise etched in stone across continents, a promise that even in the most forbidding wilderness, a traveler would find a gate, a fire, and a shared human refuge. Granite is a statement of permanence. In the sun-blasted quarries of Aswan, ancient Egyptian engineers faced a material that demanded not just effort, but absolute precision. An obelisk is a single, unbroken shaft of stone, often soaring over 80 feet tall and weighing more than 300 tons. To create one was to engage in a high-stakes performance with no room for error, a three-act drama of extraction, voyage, and elevation orchestrated under the direct command of the pharaoh. The first act unfolded in the quarries themselves, where specialized teams of stoneworkers used only stone balls and wooden wedges to perform what seems like a miracle. They would locate a flawless vein of red granite, then painstakingly carve trenches around the intended obelisk's outline directly into the living bedrock. Once isolated, the challenge was to detach this colossal piece from the earth below without cracking it. Workers would drive wooden wedges into a narrow seam at the base, then soak the wedges with water. As the wood expanded with tremendous, slow force, it would cleanly shear the obelisk free from its cradle. One unfinished obelisk still lies in the Aswan quarry today, a testament to the gamble, cracked during this final separation and abandoned where it fell. Success, however, meant a 300-ton needle now lay prone in a trench, ready for its journey. The second act was a feat of nautical engineering. The completed obelisk had to travel over 400 miles down the Nile to its destined temple, a journey impossible on land. The Egyptians built colossal, purpose-made barges from cedar wood, vessels so large they were essentially floating platforms. Getting the obelisk from its trench onto the barge was a logistical puzzle of levers, ropes, and earthen ramps. Once securely lashed down, the barge would be towed by a fleet of smaller boats, its deep draft and heavy load making it a sluggish, precious cargo vulnerable to the river's currents. The journey was a slow, ceremonial procession, a moving spectacle of royal power visible to every village along the banks. Arrival at the temple precinct marked the third and most perilous act, the raising. The obelisk now had to be moved from the horizontal barge, across land, and then pivoted from a horizontal to a vertical position onto a tiny stone pedestal, all without modern cranes or hydraulics. Evidence suggests the use of a giant earthen ramp built against the temple wall. The obelisk, still on its sled, would be dragged up this ramp, its base leading. At the summit, the base would be carefully positioned over the waiting pedestal. Then, with meticulous control, sand would be slowly emptied from sacks beneath the obelisk's raised tip, lowering the monolith inch by terrifying inch until it stood upright, its point aiming directly at the sun god Ra. This final maneuver required the coordinated pull of hundreds of men on ropes to guide the descent, a silent, breathless operation where a single snapped line or uneven pull meant catastrophic failure. The entire process, from quarry to consecration, was a symphony of specialized labor, from the who understood the stone's grain, to the shipwrights who built the barge, to the priests who calculated the perfect alignment for its shadow. Each obelisk was more than a monument, it was a captured sunbeam, a frozen ray of divine light made possible only by an organization that could turn a mountain into a needle and a river into a road. Beneath the gleaming marble and bustling crowds of the Roman Forum flowed a hidden, more fundamental truth about the city's greatness. The Cloaca Maxima, or the Great Sewer, began not as a grand civic plan, but as a simple, urgent necessity. In the earliest days of Rome, a natural stream ran through the valley between the city's famous hills, collecting runoff and waste before emptying into the Tiber River. As the settlement grew, this open channel became a festering, unhealthy problem, a source of illness and foul odors in the very heart of the community. The visionary response, undertaken around the 6th century before the Common Era, was not to avoid the problem but to master it. The early Romans, possibly under the direction of Etruscan kings, embarked on an astonishing project. They enclosed the stream, channeling it into a massive stone-lined tunnel and burying it underground. This was no simple ditch. The initial construction involved excavating deep trenches, then building walls of carefully fitted stone blocks to create a vaulted channel large enough for a person to walk through standing upright. The labor required was immense, likely drawn from the citizenry as a public duty, and it demonstrated a profound commitment to collective well-being from the very foundation of the Republic. But the true genius of the Cloaca Maxima was its capacity for growth. Over the following centuries, as Rome exploded from a regional power into a world-spanning empire, the sewer was constantly expanded and upgraded. What started as a drain for the Forum became the trunk line for an entire urban system. Secondary lines from public baths, latrines, and wealthy private homes were connected to it, creating a vast subterranean network that carried away from the densely populated city center. Maintaining this system over centuries became a sacred civic trust. The Cloaca Maxima was so vital that it was as a goddess, and its maintenance was overseen by high-ranking officials, including censors and later, a special imperial curator. Teams of workers, often stay-toned slaves under the direction of skilled engineers, would perform the dangerous but essential task of regular cleaning, navigating the dark tunnels to clear blockages of debris and silt to ensure the relentless flow continued. This long-term perspective is what makes it so remarkable. The builders of the original channel could not have envisioned the megalopolis Rome would become, yet they created a system robust and intelligent enough to be expanded for nearly 1,000 years. It was a foundational investment in public health that helped Rome sustain its unprecedented urban population by mitigating waterborne illness and creating a more livable, sanitary environment. The Cloaca Maxima did not just carry away waste, it carried away a fundamental limit to urban growth. It stands, quite literally, as the deep, enduring substrate upon which the glory of Rome was built, a lesson in how the most unglamorous coordinated efforts can uphold the most magnificent of civilizations. The silent, subterranean world of the army is a marvel of production, not just artistry. Beneath the fields near N lies a sprawling, hidden factory of the afterlife, a mausoleum complex built for China's first emperor, Qin. While the 8,000 soldiers, horses, and chariots capture our awe, the true wonder is the vast industrial coordination that created and housed them. This was not a single burial chamber, but a meticulously planned necropolis, a city for the dead constructed with the same bureaucratic precision that unified the empire. The army is housed in a series of vast, underground pits, each one a colossal feat of civil engineering in its own right. These pits are not natural caverns. They are enormous, man-made trenches, dug over 40 feet deep into the hard-packed earth. Their walls were reinforced with thick layers of rammed earth, a technique where soil is compacted between wooden forms to create a structure as durable as stone. Over these trenches, workers built a complex roof system of massive timber beams, supporting rafters and mats, which were then covered with layers of clay to seal the entire chamber from the elements. Constructing these cavernous spaces was a massive earth-moving project that required thousands of laborers working in coordinated phases, first excavating, then building the walls, and finally raising the heavy timber superstructure. But the pits were merely the warehouse. The army itself was born from a manufacturing revolution. Nearby the burial site, archaeologists have uncovered the remains of a vast production complex, a series of specialized workshops that operated like a state-run industrial park. Here, the creation of the warriors was broken down into an efficient assembly line process. Different workshops specialized in different body parts, some producing heads, others torsos, legs, arms, or hands. The components were made from standardized molds to ensure uniformity in size and proportion, allowing for interchangeability. Yet, to give each soldier a unique identity, the artisans then added exquisite hand-sculpted details, varying hairstyles, facial features, expressions, and even the intricate folds of armor and clothing. After firing in enormous, fuel-hungry kilns, the parts were transported to assembly areas where they were meticulously joined together. A separate, highly specialized workshop produced the real, functional bronze weapons, the swords, spears, and crossbow triggers, each one manufactured to lethal specification, and many still sharp today. This entire operation, from mining the clay and timber to firing the statues and forging the weapons, required a staggering supply chain and a workforce of over 700,000 conscripted laborers, organized into brigades with military-style discipline. The scale of the logistics is breathtaking, a testament to an empire that could marshal resources and standardize production on an industrial scale, all for a single, transcendent purpose: to project the emperor's power into eternity itself. A different kind of road threads through the emerald density of the jungle, a raised white line of order against the chaos of the rainforest. These are the Maya causeways, known as, or white roads, a network of elevated limestone highways that connected cities and sacred sites across the Maya world. To walk was to travel on a man-made ridge, a pathway built several feet above the swampy forest floor, paved with fitted stones, and coated in a smooth plaster of white lime stucco that gleamed under the tropical sun, making them visible and passable even during the heaviest rains. Their construction was a communal triumph. Building required the coordinated labor of entire communities, organized under the direction of a city's ruler or local nobility. The process began with surveying a straight line through incredibly difficult terrain, across sinkholes, through dense thickets, and over low hills. Once the route was cleared, workers dug parallel trenches to define the road's edges, piling the excavated earth and rubble into the center to create the raised foundation. This core was then packed down and faced with layers of stone, capped with the signature white plaster surface. The longest known causeway runs over 60 miles, connecting the great cities of and, a project that would have required a sustained, organized effort from thousands of people over many years, moving immense volumes of earth and stone without the wheel or draft animals. These roads were far more than practical thoroughfares. They were instruments of political and economic integration, physical bonds between allied city-states. They facilitated the movement of goods like jade, obsidian, salt, and ceremonial feathers, but they also allowed for the movement of armies, administrators, and pilgrims. A ruler could project his power and influence along these gleaming lines, tying outlying communities to a central capital. Perhaps most importantly, they had a profound ritual significance. They often connected major temples or led directly to sacred caves, and the natural sinkholes considered portals to the underworld. A journey on a white road was thus a ceremonial passage, a transition from the profane world of the city to the sacred realm of the gods. The causeway itself became a symbol of connection, not just between places, but between the human and the divine, a tangible line drawn by a society that sought to bring order and meaning to the vast, untamed world of the jungle. A gleaming white road through the jungle connected sacred spaces, but on the windswept northern fringe of the Roman Empire, a different kind of line was being drawn with a far more pragmatic purpose. Hadrian's Wall was not merely a wall, it was a complete military frontier system, a 73-mile-long declaration of imperial intent etched across the narrow neck of Britain. When Emperor Hadrian visited the province in the year 122, he ordered its construction to solidify the empire's northernmost border, and the project that followed became in coordinated military engineering. This was not a hasty defensive barrier thrown up by soldiers under threat. It was a planned, permanent administrative zone built by the very legions and auxiliary units who would later garrison it, transforming the landscape into a multi-layered instrument of control. The initial vision was staggering in its complexity. The wall itself was the spine, but it was supported by a deep infrastructure. To the south, a wide, flat-bottomed ditch, known as the ran parallel to the wall, creating a cleared military zone that restricted civilian movement and provided a clear line of sight for patrols. To the north, a series of defensive pits and another ditch added an extra layer of obstacle for any approaching force. The wall's construction was a feat of standardization and division of labor. The work was parceled out in measured sections to different centuries or 100-man units from 3 different legions. Each century was responsible for building a length of wall and a small fortification called every Roman mile. These were not just guard posts, they were controlled gates, allowing for the regulated passage of people and goods through the barrier, and each one was built to an identical blueprint, a testament to the Roman army's bureaucratic precision. Between each, 2 smaller watchtowers provided constant visual surveillance, meaning a sentry could always see the next post in either direction, creating an unbroken chain of observation. But the true heart of the system lay in the larger forts, strategically placed along the wall's length. These were not just barracks, they were self-sufficient towns, with headquarters buildings, granaries, hospitals, workshops, and even bathhouses. Their construction required an immense logistical operation. Timber and stone had to be transported, tiles had to be fired, and food had to be supplied for thousands of men and their families. A dedicated network of supply roads, running behind the wall, connected these forts to regional depots and ports, ensuring a steady flow of grain, weapons, and pay from the heart of the empire. The manpower itself was a coordinated blend of military specialties. The legionaries, Roman citizens, and engineering experts formed the core construction teams, while the auxiliary soldiers, recruited from across the empire, provided the bulk of the garrison force once the wall was built. This division of labor allowed construction and defense to happen simultaneously. The entire project, completed in under 6 years, represents the Roman military machine at its most efficient, capable of turning a strategic decision into a permanent, functioning landscape of stone, discipline, and control. Hadrian's Wall was less a barrier meant to stop an army, and more a sophisticated filter, a tool for managing the frontier, monitoring movement, and projecting Roman power through the very permanence of its organized, orderly presence. Isolated in the vast Pacific, the people have performed a feat of social coordination as monumental as the statues they left behind. Those towering stone faces gazing inland present a puzzle not just of engineering, but of community. How did a society with no metal, no wheels, and no large animals move scores of multi-ton statues, some weighing over 80 tons, from the central quarry to coastal platforms miles away? The mystery of transport has sparked captivating theories. One suggests they were walked upright, rocked side to side by teams pulling on ropes, a method demonstrated in modern experiments. Another proposes they were laid prone on wooden sledges or rollers, dragged across log roads. Yet regardless of the specific technique, the undeniable truth lies in the sheer scale of the human effort it demanded. Before a single statue could budge, it had to be born from the rock. The Quarry was a vast outdoor workshop, where generations of master carvers and their apprentices worked the volcanic tuff. Using handheld basalt picks, they would outline a statue directly on the quarry wall, then painstakingly chip away the surrounding stone until it was attached only by a narrow spine along its back. Once freed, it would be carefully lowered down the quarry slope, a delicate operation requiring coordinated teams with ropes and leverage. Many were then partially buried upright in pits around the quarry's base for finishing, where artisans carved the intricate details of the back, hands, and symbolic designs. This entire process, from selecting the stone to the final polish, represented a massive investment of specialized, skilled labor. But the greater organizational challenge came next: the journey. Transporting a completed, even just a few miles, was a communal undertaking of staggering proportions. It required a large, coordinated workforce, not just for pulling, but for supporting the operation. Teams would have to prepare the route, clearing obstacles and perhaps even laying down a prepared track of smoothed earth or vegetation. The pullers themselves would need to move in perfect unison, guided by rhythm and command, to prevent the precious cargo from tipping and shattering. And this workforce had to be fed, housed, and motivated for the duration of the project, which could take weeks or months for a single statue. This points to a highly structured society capable of mobilizing a significant portion of its population away from the daily tasks of fishing and farming. The food and water for these workers had to be collected, stored, and transported to the work sites, a logistical feat on an island with limited resources. It speaks of a shared cultural purpose so powerful it could align the labor of hundreds toward a single, tangible expression of identity and connection to the ancestors. They were not just statues. They were projects that defined the community, physical manifestations of a social contract that could turn a mountain into a procession. While islands and empires built monuments to gods and kings, another civilization chose to build something perhaps more profound: a perfect home for the living. The cities of the Indus Valley, like in Harappa, rise from the plains of Pakistan and India not as a collection of palaces or temples, but as marvels of coordinated urban living. Walking through their excavated streets today, you are struck not by grandiosity, but by an almost modern sense of order. This was a civilization that mastered the art of the city itself. The layout is a study in geometric harmony. Major avenues, some over 30 feet wide, run straight north-south and east-west, dividing the city into large, regular blocks. Within these blocks, a network of smaller lanes provides access to individual homes, creating a grid system that prioritized efficient movement and clear organization. This uniformity is no accident. It speaks of a powerful, centralized authority with the vision to plan entire cities from the ground up and the power to enforce that plan over generations. The coordination extended to the very materials of construction. Across the vast expanse of the Indus Valley, from the coast to the interior, builders used standardized, kiln-fired bricks. And not just any bricks, every brick, whether in a grand public structure or a modest home, conformed to a precise ratio of 4:2:1 in its dimensions. This standardization was a logistical revolution. It meant bricks were interchangeable, construction could be planned with mathematical precision, and teams of workers from different regions were all following the same blueprint. It turned city building from an art into a repeatable, scalable science. But the true genius of these cities lies beneath the streets. While other ancient cultures focused on draining water away from temples, the Indus Valley people built a comprehensive sanitary infrastructure for every citizen. Almost every house, from the largest to the more modest, had its own bathroom, often with a brick floor that sloped toward a corner drain. These private drains then connected to a citywide network of covered sewers that ran beneath the main avenues. These were not open gutters. They were carefully constructed channels of brick, with manhole covers made of stone or ceramic to allow for regular maintenance and cleaning. The system was designed with sophistication, using gravity and graded slopes to ensure waste flowed efficiently out of the city and into the river. This was public health engineered on a civic scale, an astonishing investment in communal well-being that required constant, coordinated upkeep by a dedicated municipal body. The most striking public structure is not a palace or a fortress, but a vast, watertight pool known as the Great Bath. Built with precisely fitted bricks sealed with a layer of natural tar, it sits within a complex of rooms and courtyards. This was clearly a space for ritual purification, a shared civic and spiritual center. Its construction, like the sewers and the brick standards, required a high degree of technical skill and organized labor. The entire urban fabric, from the width of the streets to the size of the bricks to the flow of the water, points to a society governed by a strong, perhaps non-royal administrative authority. This was not the rule of a single glorified king, but the power of a system, a civic idea so compelling it could coordinate thousands of people across hundreds of miles to build not for the afterlife, but for a better, cleaner, more orderly life together. In the silent, grid-like streets we hear the quiet, confident voice of a civilization that believed the greatest project of all was a well-run city. Athenian naval power was not born on the open sea, but in the controlled chaos of the shipyards. The city's dominion over the Aegean, its wealth, and its very survival during the Persian Wars rested upon a single, fragile vessel, the trireme. This sleek, fast warship, powered by 170 rowers, was a weapon of precision, but its true strength came from the astonishing industrial machine that produced it. The heart of this machine was the port of Piraeus, where the Athenians constructed monumental ship sheds, known as. These were not simple docks, but long, covered galleries built on sloping ramps that led directly into the water. Their purpose was singular: to house and protect the triremes from the destructive marine worms that would eat away at their wooden hulls. Building these sheds was a public infrastructure project of immense scale, requiring vast quantities of timber and stone, and a clear, long-term commitment to maintaining a permanent, ready fleet. Within these sheds, the trireme was built through a process of standardized craftsmanship. The hull was not a solid piece, but a complex puzzle of thousands of individual parts, each cut to exact specifications. This standardization was critical. It allowed for rapid construction and, more importantly, for interchangeable repairs during the heat of a campaign. A damaged ship could be quickly disassembled and its viable parts used to fix another, a logistical advantage that turned the shipyards into a kind of surgical theater for warships. But the materials for this puzzle came from across the known world, and their acquisition was a triumph of state-sponsored logistics. The primary need was timber, and not just any wood. Long, straight planks for the hull came from Macedonia and Thrace, while the critical, flexible ribs were made from curving oak from southern Italy. The Athenian state did not leave this to chance. It maintained permanent agents abroad to secure contracts with foreign rulers, ensuring a steady flow of this strategic resource. Then came the specialized components. The sails required vast quantities of fine linen, likely imported from Egypt or the Black Sea region. To make the ships watertight, workers needed pitch, a sticky tar derived from pine trees, which was shipped in amphorae from the forests of northern Greece. The ropes for the rigging demanded high-quality hemp. Coordinating the delivery of all these disparate materials to Piraeus in the right quantities and at the right time was a bureaucratic feat. It required a dedicated naval commissioner, and a treasury capable of advancing massive sums of money to shipwrights, who were private contractors working under state contract. The labor force itself was a symphony of specialized skills. Master shipwrights oversaw the design, while teams of carpenters, sawyers, rope makers, and sail cutters worked in concert, their efforts timed to the arrival of each shipment. This was not a seasonal effort, but a continuous, state-managed industry. The Athenian democracy understood that its sovereignty was literally built in these shipyards, and it organized its entire economy to feed them. The trireme, therefore, was more than a warship. It was the physical product of a society that could think in terms of global supply chains, standardized production, and centralized finance, turning the chaos of commerce into the orderly might of a navy ready to defend an idea. While the trireme connected an empire to the sea, another civilization turned inward, mastering its own rivers to bind a continent together. The Chinese Grand Canal is not merely a waterway, it is a liquid spine, a man-made river stretching over 1,100 miles that quite literally carried the weight of an empire on its back. Its story is one of relentless generational effort, built not in a single campaign, but pieced together section by section over 2,000 years, beginning in the 5th century before the Common Era and reaching its zenith under the Ming dynasty. The driving need was both economic and political. China's fertile south produced immense rice surpluses, while the political and military capital was often in the arid north. Moving grain overland was slow, expensive, and vulnerable to banditry. The solution was to create a water highway, a controlled channel that could float the harvest of the south directly to the granaries of the north. The sheer scale of the initial excavation is almost beyond imagining. Millions of laborers, conscripted through the state system, dug the primary channels by hand. Using simple baskets and shovels, they moved mountains of earth to create a canal wide and deep enough for large grain barges. This was not a one-time effort. Siltation was a constant enemy, requiring annual dredging by armies of workers to keep the vital artery from clogging, a perpetual cycle of maintenance that became a fixed cost of imperial rule. But the true engineering genius lay in managing the water itself. The canal traversed a vast, flat plain with subtle but critical changes in elevation. To prevent the water from simply draining away or flowing too violently in one direction, Chinese engineers invented and perfected the pound lock centuries before it appeared in the West. These locks were gated chambers that could be filled or emptied to raise or lower boats from one water level to the next, like a liquid staircase. Their operation required precise coordination. Lock keepers had to open and close massive wooden gates in a specific sequence, managing the flow of water to safely lift or lower vessels, a daily ballet of hydraulics that kept traffic moving smoothly. The canal was more than a trade route. It was the central administrative vein of the empire. A specialized bureaucracy, the Canal Commission, oversaw every aspect of its operation. They managed the legion of maintenance workers, regulated tolls and traffic, and operated the imperial grain transport system, a fleet of thousands of government barges. This system was the lifeblood of the capital. It allowed the emperor to feed his vast armies and the population of Beijing without relying on unpredictable local harvests. It also gave him a powerful tool of control, as the steady flow of southern grain could be threatened or cut off to pacify restless regions. The Grand Canal did more than move food, it moved people and ideas, blending the cultures, dialects, and cuisines of North and South into a more cohesive whole. It was infrastructure as a political statement, a tangible, flowing proof that the empire was a single, integrated organism, its wealth and stability guaranteed by the coordinated labor of millions and the unceasing flow of water they had harnessed. Scattered across the sun-bleached limestone of Malta and Gozo, a different kind of ancient writing is etched into the stone. These are the cart ruts, a sprawling, mysterious network of parallel grooves cut deep into the island's bedrock. They crisscross the landscape, running up hills, disappearing off cliffs into the sea, and intersecting in complex junctions that look like prehistoric railway switchyards. Their exact purpose remains one of archaeology's quiet puzzles. Were they for transporting massive stone blocks to temple sites, for moving soil and harvests across rocky fields, or for some ritual procession lost to time? Yet, regardless of their final use, the ruts themselves are a clear testament to organized communal labor. Creating them was a deliberate, large-scale act of landscape modification. The grooves are not random scars. They appear in consistent, parallel pairs, typically about 4.5 feet apart, with a smooth, U-shaped profile. This uniformity is the first clue to their coordinated origin. They were not worn down by countless individual travelers taking different paths, but were intentionally cut, likely by teams using stone or bronze tools, to guide wheeled carts or sledges along established, efficient routes. The scale of the network is what truly stuns. Thousands of these tracks have been mapped, covering the islands in a dense web. This was not a single community's project. It represents a society-wide system, a shared infrastructure that required agreement on routes, right-of-way, and maintenance. Imagine the planning needed to chart these paths across miles of rugged terrain, deciding where the main arteries would run, how they would navigate a steep slope, or where they would converge at a quarry or a temple complex. The labor to carve them, inch by inch into the hard limestone, would have been immense, demanding the coordinated effort of many people working in concert, likely as part of a shared social or religious obligation. The ruts speak of a culture that thought in terms of systems, that could mobilize its people not for a single, glorious monument, but for the humble, vital work of moving heavy things from one place to another, year after year, generation after generation. They are the fossilized imprint of everyday logistics, a permanent record of a society's collective effort to make their hard land yield and to connect their world, one grooved track at a time. The quiet, purposeful grooves of Malta are a record of peaceful transport. For the Assyrian Empire, however, moving heavy objects was a science of terror applied directly to city walls. Theirs was an infrastructure of conquest, a terrifyingly efficient machine designed for one purpose: to turn the strongest fortifications into dust and submission. While other empires built walls, the Assyrians mastered the art of breaking them down, and they did it through a level of military organization that turned siege warfare into a predictable, industrialized process. The sight of an Assyrian army outside your city was not just the approach of soldiers, it was the arrival of a mobile factory. Their most devastating weapon was not the sword, but the system. At the core of this system were the specialized siege engines, monstrous machines constructed with chilling foresight. Assyrian reliefs, carved in stone for their palaces, show these engines in horrifying detail. There were massive battering rams, housed in wheeled roof towers to protect the operators, their iron-tipped heads swinging with relentless, rhythmic force. There were multi-story siege towers, rolling fortresses that could bring archers to the height of the battlements. And most daunting of all, there were the siege ramps, artificial mountains of earth, stone, and timber built against a city's walls. The construction of such a ramp was a logistical nightmare made routine. It required the movement of thousands of tons of material, all while under fire from the defenders above. The Assyrians did this by mobilizing their entire army as a labor force. Soldiers were not just fighters, they were diggers, carriers, and carpenters. Prisoners from previously conquered cities were often pressed into service at the front of the work, a grim and calculated use of human resources. The work was divided into coordinated teams, some cutting timber and weaving massive wicker shields for cover, others filling baskets with earth, and others carrying those baskets in a relentless human chain up the growing slope of the ramp. This operation had to be protected, so archers provided covering fire from mobile screens, and the engineers directing the work were among the most valued specialists in the army. The true innovation, however, was in prefabrication and supply. Evidence suggests that the complex wooden components for towers and rams were not built on site from scratch. They were manufactured in imperial workshops back in Assyria, designed to be broken down into standardized parts, transported on ox-drawn carts along the empire's roads, and then reassembled like a grim puzzle outside the target city. This saved precious time and allowed for a rapid, shocking deployment of force. The entire campaign was sustained by a ruthless supply chain. Food for the army and fodder for the animals were requisitioned from the surrounding countryside or shipped from depots. Blacksmiths traveled with the army to repair metal fittings, and leatherworkers maintained the vital protective hides that covered the engines. This was a sustained, coordinated assault that could last for months, a relentless pressure that demonstrated not just martial power, but administrative stamina. The message was clear: your walls are not a refuge, they are merely a temporary inconvenience. The Assyrian siege was a spectacle of organized violence, a performance meant to break the spirit as surely as the stone. It proved that the most formidable infrastructure could be a temporary one, a machine of war so well coordinated it could literally move mountains to erase a city from the map. A different kind of mountain was being built in the high desert of the American Southwest. In the stark, expansive canyon, the ancestral people erected monumental stone structures known as great houses, like Pueblo Bonito, a sprawling, D-shaped complex of over 600 rooms rising 4 and 5 stories high. This was not a haphazard village. It was architecture as geometry, with walls aligned to solar and lunar cycles and rooms stacked in precise, symmetrical terraces. The stones themselves tell a story of coordination. Each sandstone block was carefully shaped, then set in place with a distinctive Koran veneer technique, where a rubble core was faced with beautifully fitted stone on both sides, creating walls of remarkable strength and precision. This masonry required more than skill. It required a shared vision and a disciplined workforce operating under a master builder's plan. But the true logistical marvel of is not found in its canyon walls, but in the distant mountains. The great houses required an immense amount of timber, primarily for the roof beams or vigas, needed to span the large ceremonial kivas and upper stories. The nearest forests of suitable pine and fir were in mountains over 50 miles away. Procuring these logs was an epic undertaking. Teams would have to travel for days to the highlands, select and cut down massive trees, then transport the heavy, cumbersome logs back to the canyon. The journey itself is a profound puzzle. Without wheels or draft animals, researchers believe the logs were likely carried by teams of people, perhaps using a system of ropes and carriers, or floated along seasonal waterways during rare floods. Each log represented a tremendous investment of time, energy, and planning. The scale of the need was vast. Pueblo Bonito alone required an estimated 200,000 trees over its centuries of construction and renovation. This points to something far larger than a local building project. It suggests a regional system, a web of influence and obligation that stretched far beyond the canyon's walls. Outlying communities, connected to by a network of perfectly straight roads that still scar the desert, may have contributed not just labor, but also materials and food, supporting the central, coordinated effort as part of a shared cultural or religious purpose. Canyon stands as a profound question in stone and vanished timber. It was a ceremonial and economic hub that seems to have drawn resources from across the region, orchestrating the labor of generations to build something that was less a city and more a cathedral to the sky, a testament to a society that could align its architecture with the cosmos and its people toward a single, distant source of wood. The rigid geometry of the world was an expression of celestial order, but a different kind of precision was being stamped upon the earth with military intent. In the damp, green landscape of late 10th century Denmark, a series of fortresses rose with a startling, almost mathematical perfection. These are the Viking ring fortresses, known as, and their existence shatters the popular image of Vikings as only raiders and independent chieftains. They are the physical proof of a centralized kingdom asserting its control with an ironclad, bureaucratic will. The design is instantly recognizable and unnervingly uniform. Each fortress is a perfect circle, defined by a massive, circular rampart of earth and timber. Inside, the space is divided with geometric rigor by two broad, wooden-paved roads that cross at the exact center, creating four equal quadrants. In each quadrant, longhouses were erected in perfectly symmetrical blocks, all built to identical dimensions and all aligned precisely with the cardinal points. This is not the organic growth of a trading post or a chieftain's hall. This is architecture as a standardized command, a cookie-cutter template for power imposed at strategic locations across the realm. The coordination required to build even one of these complexes was immense. Take the fortress of, or the namesake. The circular rampart itself was a colossal earthwork, requiring teams of laborers to move thousands of tons of soil. The timber needed was staggering, not just for the palisade atop the rampart, but for the precisely measured longhouses, each one a large bow-sided structure that housed warriors, craftsmen, or served as workshops. The builders were not amateurs. They were skilled carpenters and engineers working from a master plan. The longhouses were prefabricated in a sense, their massive posts and beams cut and shaped to a universal standard so they could be assembled efficiently on site. This standardization is the key to the mystery. 5 of these fortresses have been found in Denmark and southern Sweden, all built within an incredibly narrow window of time, likely during the reign of King Bluetooth in the late 900s. They are too similar, too perfectly executed to be the work of local lords. They bear the hallmark of a single, powerful organizing authority, a king who could command resources and labor from across his territory. This was a kingdom-wide infrastructure project with a clear military and administrative purpose. The fortresses were not towns, they were garrison strongholds. Their perfect symmetry allowed for optimal defense and control, with clear lines of sight and rapid mustering of forces from the identical longhouses. Their locations were strategically chosen to dominate important land and sea routes, allowing the king to project his power, secure his frontiers, and control the movement of people and goods. Building them simultaneously, or in rapid succession, was a logistical. It required a mobile, specialized workforce, perhaps soldiers themselves doubling as engineers, who could move from site to site applying the same blueprint. It demanded a supply chain that could deliver standardized timber, iron for nails and tools, and food for the workers, to multiple remote locations at once. This speaks of a kingdom with a sophisticated level of royal administration, capable of large-scale taxation, conscription, and planning. They are more than forts. They are the physical manifestation of a state being born. They represent the moment when the Viking age of decentralized raids began to crystallize into the Scandinavian kingdoms of the medieval period, a transition written not on parchment, but in the perfect geometry of earth and timber. Granite monoliths stand sentinel over the highlands of Ethiopia, silent witnesses to a kingdom that could command the very mountains. In the ancient city of Aksum, the steely fields present a puzzle of gravity and ambition. These are not simple markers, but towering, multi-story obelisks carved from single blocks of solid granite, the largest of which, though now fallen, is estimated to have weighed a staggering 520 tons. To quarry, move, and raise such a stone in a landscape of rolling hills was an act of faith in organization. The process began in distant quarries, where workers used simple iron tools and the patient force of water-soaked wooden wedges to isolate a perfect block from the bedrock. Once free, the real test began, a journey of several miles from quarry to city. This was not the flat, floodplain journey of an Egyptian obelisk on a barge. This was an overland trek across uneven, sloping ground. The Aksumites likely employed a system of rollers, sledges, and earthen ramps, a technique requiring the synchronized pull of hundreds, perhaps thousands of laborers. Ropes made from local materials would have been thick as a man's arm, and teams would have had to move in perfect unison, guided by rhythmic chants or drum beats, to inch the colossal stone forward without cracking it. The coordination extended beyond the pullers. A path had to be prepared and constantly maintained, with crews leveling the way and repositioning the rollers. Others would have been tasked with managing the immense leverage needed to steer the sledge, using levers to make minute adjustments in direction. This workforce needed sustenance, water, and shelter, implying a support system of cooks, water carriers, and camp managers operating alongside the engineers. The final act, the erection, was the most delicate. The base of the obelisk was carved with a pivot-like protrusion that fit into a massive stone socket. Using a combination of ropes from a tall, temporary wooden framework and a carefully engineered earthen ramp, crews would have slowly tilted the monolith upward, guiding its base into the socket with breathtaking precision. A single slip meant ruin. The successful raising of a stele was a public demonstration of the Aksumite kingdom's absolute authority. It showed it could mobilize, feed, and direct a vast segment of its population for a purely symbolic project, a stone needle pointing to the heavens to honor an elite individual. The stelae were more than tombstones, they were declarations in granite, proving that in the highlands of Africa, a kingdom had mastered not just trade and territory, but the fundamental physics of earth and stone through the sheer, coordinated force of its people. A dam is a wall, a statement of human dominance over a river's power. But in the mountains of Sichuan, ancient Chinese engineers proposed a radically different idea, a conversation. The irrigation system, built over 2,000 years ago and still functioning today, is not a dam at all. It is an elegant, ecological ballet of water management, a system that tames a violent river not by confronting it, but by gently persuading it to split its own power. The Min River, rushing down from the Tibetan plateau, was a source of both life and devastation for the Chengdu Plain. Its spring floods were catastrophic, while summer droughts could wither crops. The governor Li Bing, in the 3rd century before the Common Era, recognized that a simple barrier would only create a destructive reservoir of silt and pressure. His ingenious solution was to work with the river's own logic. The project's heart is the, or fish-mouth levee. This is not a solid wall, but a long, tapered dividing barrier built from woven bamboo cages filled with stones, placed strategically in the middle of the river. Its shape, like the nose of a fish, naturally splits the current. About 60% of the water carrying the heavier silt is diverted to the outer, wider channel, which continues as the main river. The cleaner 40% is guided into an inner channel, the inner river, which becomes the source for the irrigation network. This automatic, passive separation solves the twin problems of flooding and siltation in one graceful move. But guiding the water was only the first step. To get the precious inner river flow onto the higher plane, the engineers faced a mountain. Rather than going over or around it, they chose to go through with the, or precious bottleneck. This was a channel 20 meters wide cut directly through a solid rock ridge, a task that, according to legend, was achieved by heating the rock with fire and then cracking it with cold water, repeated over years by teams of laborers. The final component was the, or flying sand spillway, a low weir that uses clever hydrodynamics. During normal flow, it lets just enough water into the irrigation canals. But during a flood, the increased pressure creates a vortex that actually scoops up excess water, and most miraculously, suspended silt from the canal bottom and flings it back over the weir into the main outer river, performing a continuous, self-cleaning function. The initial construction was a monumental feat of coordinated labor, mobilizing tens of thousands of workers over a decade to reshape the very bed of a mighty river using little more than stone, bamboo, and human muscle. Yet the true testament to its brilliance is its longevity, a legacy sustained not by stone alone, but by a profound and enduring social contract. For a unique community organization formed around its care. The system's survival depended on an annual ritual of maintenance, the water-splashing repair, conducted during the winter dry season. Every year, local farmers would gather, organized by a water management council, to collectively clear silt from the channels and repair the bamboo stone structures. This was not a forced labor, but a shared civic duty, a direct investment in their own survival and prosperity. The knowledge of how to maintain the system, the precise measurements for the fish mouth, the timing of the repairs, was passed down through generations, creating a living tradition of hydrological stewardship. Therefore, stands in quiet contrast to the monumental static dam. It is infrastructure as a philosophy, a dynamic partnership with nature that requires not a single, heroic act of construction, but a perpetual, coordinated act of community. It whispers that the most resilient systems are not those that impose our will, but those that listen to the world, and then organize ourselves, year after year for centuries, to keep the conversation flowing. The sea itself could be an enemy, a relentless force that shattered coastlines and dashed ships against the rocks. To build an empire, you needed to conquer it, to carve a safe haven from the chaos of the waves. On the coast of ancient, King Herod the Great faced this exact challenge, but his ambition was not merely to find a harbor, it was to invent one where nature had explicitly forbidden it. The site he chose, Caesarea, was a stretch of open, sandy shore with no natural protection, a place where the prevailing winds and currents made anchorage a perilous gamble. To transform this hostile coast into the greatest deepwater port in the eastern Mediterranean required more than royal will. It demanded an act of hydrological defiance, a feat of engineering that turned the very sea into a building material. The core of the problem was the breakwater. In a natural harbor, a curving arm of rock shelters the water within. At Caesarea, there was no such arm, so Herod's engineers, likely drawing on Roman expertise, decided to build two of them from scratch, massive artificial peninsulas that would reach out into the open sea. The southern breakwater alone stretched over 2,000 feet into the Mediterranean. Building such a structure in deep, turbulent water was considered nearly impossible. Their ingenious solution was a revolutionary material, hydraulic concrete. This was not ordinary mortar. It was a special mix of lime, volcanic ash imported from Italy, an aggregate which possessed a magical property: it could set and harden underwater. This concrete was the key that unlocked the sea. The construction process was a breathtakingly complex ballet of maritime logistics. First, a fleet of specialized wooden barges had to be built. These barges would sail out to the designated breakwater line, loaded with the dry ingredients for the concrete and a supply of large stones. Once positioned, the real work began. Teams of divers would plunge into the water, likely using hollow reeds as breathing tubes to prepare Their task was to create a level foundation, clearing debris and perhaps placing a first layer of rubble. Meanwhile, on the barges above, workers would mix the dry concrete with seawater in large wooden troughs. The timing was critical. The slurry had to be poured before it began to set. They would dump the wet mixture directly into the sea at the designated spot, where it would sink and envelop the prepared stone aggregate. Layer upon layer, this artificial stone was poured, slowly rising from the seabed to form the submerged core of the breakwater. Above the waterline, the structure was then faced with massive, interlocking blocks of stone to protect it from the pounding waves. The coordination required was staggering. Think of the supply chain alone. The volcanic ash, known as pozzolana, had to be shipped in vast quantities from the Bay of Naples, a sea journey of over 1,000 miles. The lime for the mortar was produced locally in kilns, requiring constant quarrying and burning of limestone. Timber for the barges and was sourced from Lebanon. All these materials had to flow continuously to the construction site, a sandy beach that had to be transformed into a bustling industrial port just to build the port itself. A dedicated fleet of cargo ships, operating on a tight schedule, became the lifeline of the project. On site, the workforce was a hive of specialized labor, from the sailors navigating the supply ships and the barge pilots holding position in the swells, to the divers working in the murky depths, the mixers preparing the concrete, and the stone masons dressing the facing blocks. All of them had to operate under the direction of master engineers who could visualize the finished structure beneath the waves and direct the work with precise measurements. The harbor they created, named, was a marvel. Its inner basin was vast, with deep berths for large grain ships and a complex system of mooring stones. A towering lighthouse, rivaling the one at Alexandria, guided ships safely to its entrance. For Herod, this was more than infrastructure, it was a political statement in stone and concrete, a grand gift to his Roman patrons that proclaimed his kingdom's sophistication and loyalty. Caesarea became the bustling administrative capital and the primary gateway between Rome and its eastern provinces. The harbor stood as a testament to a brutal truth of ancient power, that the greatest monuments were sometimes invisible, lying beneath the waterline, built by the coordinated breath of divers and the relentless rhythm of supply ships. A silent, submerged will forcing the open sea to become a place of shelter. A mountain can be more than a barrier, it can be a promise written in mud and water. In the highlands of the Philippine Cordilleras, the rice terraces do not sit upon the landscape, they are the landscape, a living, breathing sculpture carved by hand over 2,000 years. This is not a ruin from a lost civilization, but a continuous, evolving dialogue between a people and their environment, an infrastructure project that has never truly ended. To call them steps is an understatement. They are entire mountainsides painstakingly reshaped into a cascading series of over 2,000 irrigated paddies, following the contours of the slopes with a fluid grace that makes the human-made seem utterly natural. The sheer volume of earth moved, stone walls built, and channels cut, all with simple wooden and stone tools, represents a generational effort of almost unimaginable patience. This was not the command of a single king or the burst of a decade's labor. It was the slow, relentless work of countless families, each generation inheriting both the terraces of their ancestors and the sacred duty to maintain and expand them for their children. The true marvel, however, is not in the stone walls, but in the invisible systems of knowledge and cooperation that keep them alive. The terraces are an integrated hydrological machine. Water is captured from the misty rainforests at the mountaintops and channeled through a meticulously planned network of canals and bamboo pipes, descending from paddy to paddy in a controlled, shared flow. This demanded a social invention as sophisticated as the engineering, a communal water management system governed by tradition and law. A council of elders, often from the families who first carved a particular terrace cluster, oversees the distribution. They establish schedules for irrigation turns, mediate disputes between neighbors, and organize the communal labor known as required for the annual repair and maintenance of the walls and canals. This work is not a tax or a forced duty, but a deeply ingrained part of the social fabric, a reciprocal agreement where every family contributes to the system that feeds them all. The knowledge required to sustain this is not written in manuals, but lived in practice. It is passed down through stories, rituals, and the direct teaching of elders to the young. A farmer knows by sight and touch the precise consistency of the mud that will hold a wall, understands the subtle signs of a leaking channel, and reads the weather patterns in the clouds that cling to the peaks. This is a cumulative, 2,000-year-old conversation with the land, a reservoir of wisdom built season by season, harvest by harvest. The terraces are therefore more than a feat of ancient engineering. They are a testament to a culture that planned in centuries, not years. They embody a philosophy where infrastructure is not a static thing you build and abandon, but a living relationship you nurture. In their shimmering, green layers, we see a different answer to the question of how societies organize, one based not on central command, but on shared necessity, generational patience, and a profound, enduring pact between a community and the mountain it calls home. A city of scrolls once rose from the Mediterranean shore. The final wonder in our journey is not a wall, a road, or a monument to gods or kings, but a monument to the human mind itself. The Library of Alexandria was more than a building. It was a grand, state-sponsored project to gather all the world's knowledge into a single, organized system. This was the ancient world's internet, a physical network of information, and its creation demanded a coordination of resources and intellect on a staggering scale. The heart of this endeavor was the Mauseon, or the Institute of the Muses, a government-funded research center unlike anything that had come before. Think of it as the world's first university, a permanent community where the greatest thinkers of the age were invited to live, work, and debate, all at the expense of the Ptolemaic kings of Egypt. This was a radical investment. The state provided salaries, free meals, comfortable lodging, and most importantly, unparalleled access to the library's collection. In return, these scholars, poets, mathematicians, and physicians produced new knowledge, curated the old, and brought immense prestige to the kingdom. But the library was the engine of this intellectual machine. Its goal was audacious: to obtain a copy of every known book in the world. To achieve this, the Ptolemies established a vast, systematic acquisition program. Royal agents were stationed in major ports and markets across the Mediterranean and beyond, from Athens to Rhodes, from Rome to Babylon, with instructions to buy any and all scrolls they could find. But they did not stop at the marketplace. An even more aggressive tactic was employed. Every ship that docked in Alexandria's great harbor was boarded by officials. Any scrolls found on board were confiscated and taken to the library to be. The originals were often kept for the royal collection, while the copies were returned to the ship's owners. This was a state-mandated, empire-wide operation of intellectual collection, a form of organized scholarship with the power of a navy behind it. Once a scroll arrived, the real work of organization began. The library grew to hold hundreds of thousands of papyrus rolls. Managing this chaos required a new science, librarianship. A chief librarian, a position held by legendary figures like the poet Callimachus, oversaw a staff of scribes and conservators. They developed systems to classify the scrolls by subject and author, creating the first known library catalog, which filled 120 scrolls by itself. Teams of skilled scribes, working in scriptoriums, were engaged in the endless task of copying texts to preserve them and to create duplicates for circulation. The library complex itself was a purpose-built infrastructure for knowledge, with storage rooms designed to protect the fragile papyrus from Alexandria's humidity, reading rooms for scholars, and covered walkways for discussion. The funding for this entire enterprise flowed directly from the royal treasury. The Ptolemies understood that knowledge was power, and that hosting the world's brain trust cemented their city's status as the global capital of culture and learning. This was not a philanthropic hobby, it was a strategic national project. The coordination extended to the very process of verification. Scholars debated the authenticity of texts, comparing different copies to establish definitive versions of Homer's epics or the plays of the great tragedians. They translated foundational works, most famously commissioning 72 Jewish scholars to translate the Hebrew Bible into Greek, a project known as the Septuagint. This massive, collaborative effort required housing, feeding, and managing the translators for an extended period, a logistical feat in itself. The Library of Alexandria, therefore, represents the pinnacle of a different kind of ancient coordination, the coordination of curiosity. It was a physical hub where the state orchestrated the flow of ideas across continents, funded the quiet labor of copying and cataloging, and sustained a permanent community dedicated solely to thought. Its legacy is a reminder that the most enduring infrastructure is sometimes not made of stone, but of parchment, organization, and the collective, organized will to understand the world. These threads of stone and water, from pyramids to canals, weave a common tapestry of human ambition. While each project is a unique marvel, they all reveal shared patterns, a recurring blueprint for how ancient societies organized themselves to achieve the impossible. At their core, these endeavors were rarely just practical. They were instruments of power, profound statements made tangible. For a pharaoh, a pyramid was a machine for resurrection, a guarantee of eternal rule. For a Roman emperor, an aqueduct was a gift of civilization that bound the populace's loyalty to the state. For the Inca, The road system was the sinew of control, allowing a central authority to govern a patchwork of cultures across impossible terrain. Whether serving a god, a king, or an imperial bureaucracy, these projects consolidated authority. They demonstrated a ruler's ability to command the landscape and the labor of thousands, making abstract power visible and undeniable to every citizen who drank from a fountain, walked a paved road, or gazed up at a monument. Behind this display of power lay a relentless focus on logistics, a series of universal puzzles every ambitious society had to solve. The first and most immediate was the human puzzle. How do you feed an army of workers, not for a week, but for decades? The answers were as ingenious as they were varied. The Egyptians used the Nile's flood cycle, employing farmers during the idle season and sustaining them with state-run bakeries and breweries. The Romans often used their own legions, turning soldiers into a self-sufficient, disciplined labor force. In the Andes, the Inca system created a rotating labor tax, where communities fulfilled their duty to the state in manageable shifts, ensuring fields were still tended back home. Housing this temporary city of workers was another challenge, leading to the planned settlements at Giza or the worker villages near great building sites, all requiring their own mini-infrastructure of water, shelter, and sanitation. Then came the challenge of materials. A vision in stone often began in a distant quarry. Creating a reliable supply chain for specialized materials was a feat of economic coordination. The Romans sourcing volcanic ash from Italy for Herod's harbor at Caesarea, the Athenians importing linen from Egypt and timber from Italy for their triremes, the Khmer moving millions of tons of earth for their reservoirs. These were not local shopping trips. They required long-term contracts, secure transport routes, and often a royal monopoly on critical resources. This drive for efficiency led to one of the most powerful organizational innovations, standardization. The uniform bricks of the Indus Valley, the interchangeable parts of Athenian warships, the identically spaced on Hadrian's Wall, all speak to a central truth. To build at scale, you must make the process repeatable. Standardized measurements, techniques, and components allowed for the division of labor, faster construction, and repairs by anyone familiar with the system, turning a monumental task into a series of manageable, identical steps. Perhaps the most subtle pattern is the commitment to maintenance, the understanding that a project is not finished when the last stone is laid, but when it finally crumbles. An irrigation canal silts up, a road surface wears away, a wooden bridge rots. The societies that left a lasting mark planned for this. They established permanent bureaucracies, like the Roman, for the water supply or the Ming dynasty's Canal Commission. They embedded maintenance into the social fabric, like the annual community repair of the irrigation system or the Inca village responsibility for renewing their grass bridges. This long-term perspective, the willingness to invest labor and resources year after year, century after century, is what transformed brilliant construction into enduring infrastructure. It shifted the goal from a single triumphant moment to the sustaining of a perpetual function, a rhythm of care woven into the calendar of the civilization itself. These silent stones and forgotten canals whisper a truth louder than any single invention. They tell us that the greatest material of the ancient world was not granite or bronze, but the human capacity for collective action. The real wonder is not the aqueduct arch or the pyramid slope, but the invisible architecture of society that made them possible. These projects were the birth certificates of the state itself, proving that early civilizations could think in terms of decades, command resources across continents, and synchronize the labor of thousands toward a single, monumental goal. They mastered the art of the long game, investing not in quick returns, but in legacies meant to outlast dynasties. This required a new kind of imagination, the ability to see a mountain not as an obstacle, but as a quarry, a desert not as a wasteland, but as a canvas, and a river not as a boundary, but as a tool. What we have walked through are 30 variations on a single theme, the theme of organization. It was the meticulous ledger of the grain scribe at Giza, the standardized brick of the relay runner's flawless handoff on the Inca road, and the shared water schedule of an elder. These were the systems that built the symbols. They reveal that our ancestors were not just dreamers of big things, but brilliant managers of complex realities. They solved the timeless puzzles of how to feed a temporary city of workers, how to move a mountain of stone without cracking it, and how to maintain a delicate balance with nature for centuries. Their legacy is not frozen in the past. It flows in the water of cities that still drink from Roman channels. It hums in the supply chains that feed our modern world. And it lives in every skyscraper raised by coordinated crews following a shared blueprint. These ancient coordinators remind us that behind every enduring mark upon the earth, there stands not just an engineer's calculation, but a society's agreement, a profound and sustained act of working together. So, as the echoes of these projects linger in your mind, we would love to hear which one resonates most with you. Was it the cosmic city of the whispering lines or the living machine of? Let us know in the comments below.